So, welcome to final exam review. So the final, of course, will be on Thursday, starting at noon Pacific, and we'll spend today and tomorrow, like we did with the midterm, going through a lot of example problems to review a lot of the stuff that we've done throughout the course. So I want to start with some nice, chill examples of some graph theory. So we've seen some problems like this already, and possibly on the homework and the practice exam of the following form. So, does there exist a graph with some prescribed number of vertices, let's say 6 vertices, and also with prescribed degrees for each vertex? So let's go through a couple examples of these kinds of problems and see what kinds of techniques we can use to figure them out. So does there exist a graph with 6 vertices of degrees 1, 2, 2, 4, 5, 6? So there's a number of different things that you can look for in these problems. Some of them are the kinds of facts that we've proved about degree in our course of studying graph theory. But you can start with some quite simple observations about graphs and how they work. So let me emphasize. So I try to write this when it's particularly important, but when we say graph, we always mean a finite, simple, undirected graph. So undirected means that the edges have no directions. Finite means there's a finite number of vertices. And simple, you will remember, means that there are no loops or multiple edges. And the reason that I'm pointing this out right now is that in this particular sequence of degrees for each vertex, we have a 6 at the end. And in a simple graph with 6 vertices, that is impossible. Because if we have 6 vertices, then what is the maximum degree of a vertex? The maximum is, the most it can possibly do is connect to all the other vertices, and that will only give you 5 edges. So in a graph with 6 vertices, the degrees can be at most 5. So in this case, no, there does not exist a graph with these degrees. Let's do another example. Does there exist a graph with 6 vertices of degrees 0, 1, 2, 3, 3, 5? So now we don't have that same problem. We don't have any vertices of degree greater than 5. So we will have to look for anything else that could go wrong. And here is another basic observation that you can make. You cannot have lots of vertices of very big degree and also lots of vertices of very small degree. Basically because you have to, if you have some vertices with very high degree, then they have to be connected to almost all your other vertices, and that prevents you from having lots of vertices of low degree. So in this case, the way we can be very concrete about this is that, again, in the case of 6 vertices, we have a vertex of degree 5, let's say it's this one, and degree 5 means that it has to connect to all the other vertices. There's only one way that can happen, because there's only 5 other vertices to possibly connect to. So we know our graph has to have at least these edges, but now already you can see that there's no vertex of degree 0. because since this guy has to connect to every other vertex has to have at least one edge. So can't have degree 5 and degree 0 at the same time. So in this case, the answer is again, no. Let's have another example. What about vertices of degree 1, 2, 3, 3, 4, 4? So there's no vertices that have too many edges altogether. And let's see, we have 2 vertices of degree 4. But since they're not degree 5, they're not connecting to every other vertex. So I don't think there's anything we can say about that. So let's go ahead and try to draw a graph and see what happens. So we have one vertex of degree 1. So it's going to be hanging off the edge. And then we have some other vertices, and we want to make the degrees 2, 3, 3, 4, and 4. So let's just start drawing some things. This will be our degree 2 vertex. So this needs to have degree 3. And then these 3 need to have degrees 3, 4, and 4. And somehow it seems like there's just not enough edges to make that happen. So it seems like it's unlikely that we're going to be able to do this. So let's look more carefully about this sequence of degrees and see if there's anything we can say. And remember, so let's recall the couple of theorems that we proved about degree when we were talking about graphs. We proved a couple of theorems, namely the handshaking theorem that the sum of the degrees of each vertex equals twice the number of edges. And we could already do this computation and see that something has gone wrong, but maybe an even more direct thing to say is that we proved it as a corollary that we will always have an even number of vertices of odd degree. And in this case, we have 3 vertices of odd degree. That is not an even number. And so our corollary is telling us that no graph can exist with these degrees because it has an odd number of vertices of odd degree. Finally, let's do one more example. 1, 2, 3, 3, 3, 4. So in this case, we don't have too many vertices of high degree. We don't have too many vertices of low degree. We don't have any vertices of degree greater than 5, and we have an even number of vertices of odd degree. So we're not seeing any obstructions. Let's go ahead and try to draw an example. Again, we're going to have a vertex of degree 1, so let's just draw that like that. And then let's try making this the vertex of degree 4. So if we draw a bunch of points over here and connect them all, then these are all degree 3. and this is degree 4. And we're missing we need to add one more vertex, which is degree 2. And we can see maybe that if we hang that off of this is no longer degree 1, but this becomes degree 1, and this is degree 2. So yes, in this case, here is an example of a graph with these degrees. And in the case that there is an example, to prove this, you basically want to draw an example. And there's no absolutely systematic way of doing that, but you can probably do it without too much difficulty if you basically just start playing around and drawing some graphs. Draw some graphs, see what goes wrong, try to fix it. And also, follow some general rules of thumb, like the vertices of high degree should all be connecting up with each other, and the vertices of low degree should all be hiding somewhere off in the corner. So this is maybe not entirely all, but this is almost all the ways that we know how to attack these kinds of problems. Before we move on from graph theory, I want to sneak in a part of a problem from the practice exam that I think is slightly tricky. So here's another example, or another problem. Prove that the edge connectivity of the complete graph K5 is equal to 4. So there was a problem on the practice exam, which was the solutions that have been posted. So you can go and look at them if you want, and you will find that this was a component of one of them. And in the course of this proof, we want to prove that the edge connectivity of K5 is equal to 4. So let's recall what this means. Recall the edge connectivity of G is equal to the minimum number of edges needed, minimum number of edges we can remove to disconnect the graph. So let's draw our graph K5. It has 5 vertices all connected to each other, like so. And we want to prove that the edge connectivity is 4, meaning that the minimum number of edges we can remove to disconnect this graph is 4. So for starters, note that 4 edges do suffice to disconnect the graph, which is to say that the edge connectivity is at most 4. For example, if we delete all the edges around a single vertex. So, for example, how big is my eraser? Oh, very small. For example, if we choose this vertex at the top and just delete all of his edges, then the graph is clearly disconnected because this vertex has been separated from everything else. So this is an easy upper bound on the edge connectivity, and we're using this general rule that the edge connectivity is always less than or equal to the minimum degree of a vertex. It is not always equal. We've seen examples of that, but it is always at most the minimum degree of a vertex. Okay, so I should say K5 here. So we want to show this is equal to 4. We've shown it's at most 4, because 4 edges suffice. To show that it is equal to 4, we want to show that 3 edges do not suffice. And how can we do this? This is the part that is potentially a little bit trickier. So maybe you have come up with other ways to do it than this, but here is a way that seems reasonable to me to do this, which is to note we can draw. So remember that connectivity is all about paths. 2 points are connected if there is a path between them, and a graph is connected if there is a path between any 2 points. So in order to show that 3 edges do not suffice, let's think about all the paths in our graph between some pair of points. And in the case of the complete graph, it's symmetric in the sense that all of the vertices essentially look the same. So we can choose any one vertex and any other vertex and consider the paths between these vertices, and it'll basically be true for all the other pairs as well. So what we can show is that we can draw 4 paths. Let me call this A and this B. 4 paths from A to B that have no edge in common. And that proves what we want. That proves that 3 edges do not suffice, because in order to disconnect the graph, we need there to be some pair of vertices that has no path between them. And this is saying, if you can find 4 paths that have no edge in common, you need to disconnect all these paths, and if they have no edges in common, you need to cut at least 4 edges. So this will tell us what we want to know, and this is because we can take the direct path, so the length 1 path. So remember, length is the number of edges. The length 1 path from A to B is just traversing this single edge. So that's 1 path. And then there are 3 more length 2 paths, one via each of the other 3 vertices. So besides A and B, there are 3 more vertices in our graph, and there is a unique length 2 path through each of those vertices. So like through this vertex, there is a path of length 2 that goes like this. And there's another one that goes like this. And there's another one that goes like this. And those are 4 paths that have no edge in common. And the fact that they have no edge in common, you can see by inspecting them on the graph, but you can also see because they are uniquely determined, an edge is uniquely determined by its endpoints. And if you think about the edges that can be in these paths, they cannot share both endpoints. Because in this case, the endpoints are A and B. And in this case, the endpoints are either A or B and a unique one of these other 3 vertices. So that shows that there are 4 paths with no edge in common, and that shows, as we wanted, that the edge connectivity is exactly 4. 3 edges do not suffice. And you should be able to think about how to adjust this argument to do it for any complete graph, not just K5.